technical difficulties we had at the beginning to get started, but we're ready now. So I want to welcome you to this MCA webinar on advances in multi-access industrial Ethernet-based motion control systems, presented to you by ACS Motion Control. My name is Carrie Hitchner, and I'm the Marketing Manager for the Motion Control Association. This webinar will be recorded, and an email with a link to the recording will be sent to you in the next 24 hours. If you have any questions during the webinar, please send them via email. I'd now like to introduce our webinar presenter today, Jason Gorgas. Jason is the General Manager for ACS Motion Control. He received his bachelor's degree in electrical engineering and minor in business management from the University of Minnesota. Jason went on to receive a master's degree in electrical engineering from Arizona State University, focusing on digital signal processing and control systems. After working as an engineer at Honeywell Flight Control Systems, Jason joined ACS Motion Control in 2007 and currently resides near Minneapolis, Minnesota with his wife. He enjoys spending time with family and friends and being active in his local community. This webinar is sponsored by the following companies. ACS Motion Control is a world-class provider of high-end multi-access motion control systems. ACS products are uniquely designed to meet the needs of equipment manufacturers with the highest throughput and highest precision requirements, such as semiconductor wafer inspection and metrology equipment, flat panel display manufacturing equipment, electronic assembly equipment, and more. Founded in 1985, ACS Motion Control's core competencies include servo algorithm development, real-time operating system development, advanced electronics design, Windows-based user interface design, and technical support of demanding motion control applications. ACS's international headquarters is located in Israel, and application support and technical sales offices are located in the USA, China, and South Korea. Our next sponsor is AdLink Technology. AdLink provides a wide range of digital imaging products for industrial, medical, and transportation industries and OEM machine vision applications. Products include PCI Express frame grabbers and compact vision systems for various interfaces. AdLink is a global company with headquarters and manufacturing in Taiwan, R&D and integration in Taiwan, China, and the USA, and an extensive network of worldwide sales and support offices. Our final sponsor is Servo2Go.com. Servo2Go.com is an online e-store distributor of automation and motion control products, including servo motors and drives, stepper motors and drives, automation and motion controllers, positioning stages and actuators, feedback devices and HMIs, and operator displays. I want to thank all of our sponsors again, and now I would like to hand it over to Jason. Jason, please take it away.
Okay, thanks, Carrie. All right, so I'll go ahead and get right into it. I have an agenda here for the presentation, and then we'll get into the slides. So for this presentation, we're going to be discussing basically the architectures for multi-axis industrial Ethernet-based motion control systems. We're going to present kind of a typical architecture. I will discuss a few technologies that have been developed by either our company or companies that we've partnered with, specifically designed to meet the needs of very high-end, extremely demanding motion control applications. We'll give 3 examples here, generic examples for motion, demanding motion control applications and the technologies designed for each of those to meet the needs of each of those. And then towards the end, we'll actually incorporate those technologies into an advanced architecture for multi-axis industrial Ethernet-based motion control. So let me go ahead and start by explaining the standard or typical architecture for industrial Ethernet-based motion control. Industrial Ethernet-based motion control and industrial Ethernet networks are pretty prevalent today in the industry. There are a variety of industrial Ethernet protocols, but in general, the architecture consists of a manager of the network. Many times that's a PLC. It could be a specific dedicated box that has a PLC that's managing the network that manager of the network might also actually be not a PLC, but just a process running within a PC, which would actually represent a PC-based control for an industrial Ethernet network. Now, the network manager actually then typically communicates to the user interface, which could be some applications running in a Windows or a non-Windows environment. It might be another PLC, it might be HMI or some actual physical user programmable device. That's one responsibility of that network manager, to communicate with other devices. But on the network itself, the network manager is communicating with, from the motion control standpoint, it's communicating with the motor amplifiers or motor drives. So in this context, I'll be using the term motor drive to actually encompass the product which does the real-time control algorithms, the power amplification, basically everything that's needed electronically to operate an electric motor. And in many cases, those drives and motors are actually combined into a single product, and in some cases, they're actually separate products. So traditionally, these motor drives, you have a single box that encompasses the processing electronics for running the motor. And here in this diagram, we simply have show a few different examples of drives showing connection, control of various types of motors. What's not shown in this diagram are the additional nodes, which might be process specific, that aren't actually motor drives, but might be general purpose IOs, or again process specific IO devices in addition to those motor drives. So this is kind of the basic architecture of an industrial Ethernet network. However, this architecture is somewhat limited when you actually run up against very high precision, high performance applications, and that's what we're going to be discussing next. So the next slide here in the show is presenting a few challenges for one type of high performance application. We're talking in this case about high-resolution wafer inspection, semiconductor wafer inspection. So when you're controlling a motion system for a high-resolution wafer inspection machine, there are two big challenges for a traditional industrial Ethernet-based architecture. One of them is that when you control axes over a network, you actually can run into the limitation of the network's synchronization and determinism capabilities. So we give a simple example here. Assume, like the drawing shows here, you have a gantry system. A gantry system in this case is described as an X prime type of motion system. And ideally you are controlling the X and the X prime linear axes that are in parallel with one another. You're controlling them ideally to be at the same position at the same time. So ideally you want the X and the X prime to be at the same position at the same time. However, if you're controlling those axes as independent axes over a network, the network actually is subject to synchronization limitations. And at least for the industrial Ethernet network that our company is familiar with, which is EtherCAT, the synchronization or the network jitter, how well you can synchronize the sampling and events of various network nodes, it's generally limited to 100 nanoseconds or 0.1 microsecond. So if we take an example of this XX prime linear gantry, and we're moving it along at 1 meter per second, ideally. If the X and X prime are moving at 1 meter per second, and you're using independent drives to control each axis, that 100 nanoseconds actually can induce an artificial error of 100 nanometers, because you take 1 meter per second multiplied by 100 nanoseconds. That basically means that jitter can introduce an artificial error of up to 100 nanometers. So if you're controlling a stage where the resolution is down to the nanometer or even sub-nanometer, it becomes quite apparent that controlling multiple coordinated axes over a network, which are mechanically coupled in this case, becomes problematic. A second control challenge for this type of application is achieving the very high resolution, which in today's most demanding equipment or most advanced inspection equipment is generally sub-nanometer positioning resolution. And not only does that need to be the resolution, but that might also be the level to which the motion stage has to be in position when you're not moving. So you have to actually be hold position to within under a nanometer, for example. That's a typical requirement. However, those systems also may require speeds of up to 1 meter per second, for example, and very high accelerations. So you now in today's equipment are seeing such fine resolutions, but still the envelope is being pushed in respect to the speed and the acceleration capability of the motion system, which basically requires voltage and current that corresponds to voltage and current requirements for the motor drives, and specifically the amplifier circuits inside of them. So these are two common challenges, and I'm going to next present some technologies developed to address these challenges. The first one, again, dealing with the issue of network synchronization jitter, or deviation between ideal events from one node to another in a network. A technology that's been developed to overcome that is the idea of actually a multi-axis drive, or a multi-axis drive node on the network. So again, here you see in this diagram on the left an example of 3 single-axis drives which might be used to control an X prime Y gantry system using, again, the traditional single-axis drive approach for industrial Ethernet-based motion control. So some companies have actually begun to develop multi-axis drives, our company, of course, being one of those. And the multi-axis drive gives you benefits, a few benefits. One of them is that, of course, it's eliminating the actual jitter that you would see in the network-based control, which I presented an example of 100 nanoseconds of network jitter when you're using a single processor and a single drive to control all of those axes. You're now looking at a sampling and update jitter of 1 nanosecond or less. So effectively eliminating that jitter between axes. And because of that elimination of jitter, we can now implement very sophisticated algorithms to control those types of mechanical systems, a linear motor gantry in this example. A term that's commonly used is MIMO, multiple input, multiple output control algorithms, and these have been proven to be very effective at controlling mechanically coupled structures like XX prime Y gantry stages. So executing that type of control algorithm is the multi-axis drive node, which would be running off of a single processor to handle all of the real-time control algorithms. That's very well suited for that type of control. I'm sorry, I had a window pop up on my screen here. So in any case, the execution of a multi-input, multi-output control algorithm is very important for a multi-axis drive to achieve the performance needed, and also you reduce cost actually by implementing a multi-axis drive. You, instead of having multiple processors, not only for doing the servo loops, but also multiple processors for handling the network communication, a multi-axis drive uses a single processor for doing the control loops and a single processor for doing the industrial Ethernet communication. So it's a very cost-effective way to actually control precision multi-axis stages. So that's one technology developed. The next one is how to handle that demand for extremely fine resolution while maintaining the capability to move the motion system at very high speeds and high accelerations. So I'm presenting here actually just an introduction to a few drive technologies. The first one, Nano PWM, this is actually a proprietary technology developed by our company, by ACS Motion Control. That was actually the primary subject of the last webinar we did with the Motion Control Association, so I'm not going to give a lot of detail on that here. However, certainly recommend anybody that's interested to look up our last presentation with the Motion Control Association on Nano PWM. The Nano PWM technology is basically a unique PWM drive technology that enables sub-nanometer positioning resolution with a PWM drive, and that's traditionally been only capable or only possible with linear amplifiers, not to confuse linear meaning rotary or linear motion, but actually a linear amplifier which operates the power transistors in the linear region of operation as opposed to on and off type of operation that's common to PWM. So Nano PWM is a unique PWM technology developed for sub-nanometer positioning applications, and so that enables this sub-nanometer requirement, but also has the benefits of high power efficiency common to PWM amplifiers. And so these types of amplifiers are already available with power ranges into the several kilowatts, which is necessary to move relatively large motion stages. Another drive technology that's critical for maintaining that resolution is actually being able to process the position feedback information at a necessarily high resolution. So on ACS products, we've introduced a very high frequency encoder input specifically designed for reading sine-cosine signal type encoder signals from either a laser scale or interferometer type encoder. A common type of encoder in the industry is a magnoscale, and in that case you would have a signal period, for example, of 137.5 nanometers, which is actually 1/4 of the 550 nanometer light wavelength. But if you assume that as the fundamental signal period of the encoder, then the resolution can be up, down, all the way down to the picometers range, which is really quite incredible. And by having a 10 megahertz frequency sine-cosine interpolation with 16-bit interpolation or multiplication, you can achieve these picometer or on the order of several picometers resolution while moving the stage at up to 1 meter per second. So it's just really quite amazing that you can move and track the motion of a stage at 1 meter per second or more when you're actually counting the resolution at which you're controlling that stage is on the order of picometers, which is 10 to the minus 12th meters. So just really an amazing capability to have that type of dynamic range or that type of resolution. There's a diagram here just showing the idea behind sine-cosine interpolation, which is you take a raw analog signal composed of sine and cosine waves, and through some electronics and some mathematical calculations, you can actually resolve a position with down to an incremental signal. So that's the idea behind high-frequency sine-cosine interpolation. The third technology that I'm mentioning here is, it's actually related to the second one, but it's the idea of having multi-feedback control and on-the-fly feedback switching. So again, for these high-resolution wafer inspection stages, a requirement that we see more frequently is to control the stage or control the system, not only based on the encoders which reside on the motors themselves, but also to use a feedback signal that represents the position of the load, which in the case of a wafer inspection machine is oftentimes the wafer chuck. So you actually may have multiple feedback devices that are providing information, and the control system may be required to process all of those feedback signals simultaneously, doing what's called a dual loop type of control, where you close a position loop on one encoder and the velocity and the other inner loops on a different encoder. That's one common requirement. Another one is actually the ability to switch between those feedback signals depending on the range or which range of operation you are within the machine itself. So over a certain range of the machine, you might be controlling using feedback from a very fine resolution encoder, and over a larger, maybe more towards the outsides of the machine, you're using a lower resolution encoder. And so the capability to take in those multiple encoders or feedback signals and be able to switch between them smoothly on the fly, it's a new technology that's becoming available on certain drive hardwares. Okay, so that's the first application I wanted to present. The second one, and the challenges associated with it, is high precision laser cutting. And we're talking specifically about laser cutting with feature sizes on the order of micron and even sub-micron. And so we see that type of application with glass cutting or PCB circuit board cutting. It's not necessarily that it's not for metal cutting, but in many cases metal cutting or just fabric cutting, let's say, might not have that same level of precision. So our company's experience is primarily in glass and PCB laser cutting, although these ideas are of course expandable to other types of laser cutting, laser welding, laser processing applications. So the challenges to an industrial Ethernet-based control system for this type of application, one of them is how do you synchronize the control of the laser to the motion path itself that's being controlled over that industrial Ethernet network. The second one is how do we actually minimize the servo error or the following error while maintaining high throughput. And again, when you're talking very fine resolution features for laser cutting applications, the corners, the radiuses of the corners that you're traversing in the motion path can be very, very small, which of course represents then very high accelerations for the component axes involved in the motion. Okay, so let's look at some technologies developed here. Specifically, our company has developed a piece of hardware for actually synchronizing output signals to motion that's controlled over the industrial Ethernet network itself. There are other companies that offer, I guess, similar products, but I'll mention a few points relevant to a product that ACS Motion Control has developed called the Laser Control Module. And this module is actually an industrial Ethernet node itself. It's actually, you can think of it as a special type of I/O node, where the I/O, specifically the outputs from that node, are very high-speed digital signals. And those digital signals can be, as explained in the second bullet here, they can be pulse width modulated signals, pulse frequency modulated signals, or just general position-based outputs, so pulses that occur at predefined positions. So by having a device that utilizes the synchronization capability of the network, you're able to synchronize those outputs at a very very fine level with the actual motion itself. And by having those outputs coming out of a dedicated node on the industrial Ethernet network, it then makes sense that those outputs can actually be assigned in software to any axes that the developer defines on the motion control system. So there may be certain applications where you have a multi-axis control system, and in some operation modes you wish to generate digital signals to control a laser based on XY motion. And in other cases you may want to generate the pulses based on YZ motion. And maybe in other cases you want it to be based on X, Y, Z, theta motion. So by having a dedicated node to generate these signals based on the multi-axis path, you can actually assign dynamically those pulses to the corresponding axes for which the motion is occurring. So a laser control module, a dedicated industrial Ethernet-based node for controlling lasers based on motion paths. That's one technology developed to solve the challenge mentioned. And the second challenge mentioned again being how do we deal with minimizing error as we are moving through motion paths that have smaller and smaller corners and feature sizes. This type of motion path has generally, it's been for quite a long time in the industry that control companies have offered look-ahead algorithms, which actually slow down the motion. If you take the example of an XY, you slow down the motion as you go around corners in XY, such that the accelerations and the velocities of the X and Y individual axes are reduced. So look-ahead is a fairly common and prevalent feature in the motion control world. But what is relatively new for many motion control companies is the idea of implementing look-ahead to not only limit the velocities and the accelerations of the component axes, but to also start to limit the higher order motion behavior, which in this example we're discussing a third order look-ahead, which in the standpoint of the motion controller, you're actually limiting the commanded jerk of the component axes. So not only are you defining the limit of velocity and acceleration for each axis, but you're also defining the allowable jerk, or the derivative, the buildup of acceleration, which is also commonly referred to as S-curve. So by using a look-ahead, which implements S-curve limiting or jerk limiting, you can actually further smooth the motion path, and there's very little impact on the overall throughput of the path itself. And in many cases, as the example, or as the drawings show here on the upper right, there's we're showing an example profile from an application, cutting holes at small holes at the corner of a square, for example. And the lower images are actually showing the error or the jerk that's induced by that profile. Specifically now on the bottom, we're looking at the green and the blue are representing the X and the Y jerks, respectively, as a function of time. So you can see that for this application, given the limits of acceleration and velocity for X and Y, it took this motion profile approximately 1.7 seconds to complete. On the left, you see with a standard look-ahead algorithm, and on the right, you see a look-ahead algorithm where the jerk is actually being limited, or what's referred to as a third order look-ahead. So you can see that it does extend the path, or the time for which the motion takes to complete by the order of maybe a few milliseconds or tens of milliseconds. But the induced errors are actually much, much lower, which can allow the developer, the motion system programmer, to actually potentially further increase the velocities and the accelerations, resulting ultimately in better throughput as well as reduced falling error, which means basically a more accurate cutting or a more accurate welding for the application. So third order look-ahead is an advanced feature that's actually a function of the motion controller, the industrial Ethernet network controller itself. All right, the third application I'll introduce today is high throughput pick and place equipment. So the example here, we're actually going to be talking about a SMT assembly equipment, or sometimes referred to as chip shooters, where you're actually populating circuit boards with a high number of surface mount components. And these machines are measured, basically their performance is measured in terms of accuracy at which the picking and placing can be done, but they're also measured in terms of their throughput, oftentimes in parts per hour. And today's latest generation chip shooters or SMT pick and place machines can be in the several tens of thousands of parts per hour pick and place, which is really quite incredible. So the challenges for this type of application for an industrial Ethernet-based control system, one of them is how do you actually handle communication between the controller and the host applications, which might be handling vision and other external sensors, processing information from those other external devices, and feeding that information to the motion controller itself. These machines often are picking apart, moving over a camera to identify the orientation of the part, and then adjusting the actual final placing coordinates based on the information received from the camera. And so that's done very, very fast and requires high-speed communication between that host application managing the camera information and the motion controller that's commanding the motion. How do we address high-speed communication for that type of application is one challenge. A second challenge is these architectures or these machines take advantage of the architecture of industrial Ethernet in that it can be very beneficial to mount the motor drives out on the moving machine itself. Why not take advantage of the distributed nature of industrial Ethernet and put those motor drives out on the moving machine instead of sitting in a control cabinet outside of the motion system, which requires lengthy cables and expensive cables. It can be much more elegant to actually place the motor drives out on the moving machine itself, on the moving carriages, to reduce wiring and reduce cost and improve efficiency. However, when you have industrial Ethernet devices that are moving at high accelerations, those devices might be subject to cable failures because you're constantly accelerating and dragging those cables and also the connections on the actual industrial Ethernet devices, the drives themselves. So how to be robust to potential failures or even intermittent failures of cables and nodes on an Ethernet, industrial Ethernet network, that's another challenge for this type of application. And really for any application in which the industrial Ethernet-based devices are mounted remotely on a moving machine. So let's talk about how to solve the first challenge. I have here a diagram that basically is showing, again, from an earlier slide where we presented the typical industrial Ethernet-based control architecture. A common way to communicate between a standalone controller, could be a PLC or a motion controller, and a host PC is over Ethernet. Now, many companies have developed PC-based controllers in which you plug a card into a PC and the communication between the controller card and the PC applications is over PCI bus. But even a PCI bus with dual port RAM can be a limitation or a bottleneck in terms of communication throughput. So what ACS and a few other companies are offering currently is actually what's called a soft controller, where the controller is actually running on one of the cores of a multi-core PC. So an enabling technology is actually multi-core PC processors, and the ability to run a real-time operating system on one of the cores, to basically consume one of those cores, and instead of running Windows on that core and a process within Windows or even a real-time kernel in Windows, instead of doing that, you can actually run a dedicated real-time operating system on that core, and then you can guarantee the synchronization and the determinism required for real-time industrial Ethernet-based motion control. And the communication then between that core and the other cores in the PC, which are running Windows or some other host OS, the communication between those cores is actually, there's two channels. There's both virtual TCP/IP, which is effectively identical to standard physical TCP/IP. Doesn't really offer much for improvement of throughput. But shared RAM, shared memory communication between those cores is actually the key. It's what enables a much higher throughput communication than what's even been previously available through those PCI-based controllers that I discussed. So shared RAM communication, interprocessor communication is basically the fastest commercially available communication that you have in the marketplace today. So by implementing a motion control architecture where the controller itself is actually one of the cores of a multi-core PC, you can leverage on that shared RAM channel, and that's what allows the extremely high throughput between the controller and the host application itself. Of course, when you're implementing the motion controller inside of the PC, then that motion controller also consumes the physical Ethernet port or ports of that PC in order to actually physically communicate with the industrial Ethernet network, and that's what's mentioned here. The LAN port is consumed by that soft controller in addition to a dedicated PC core. All right, so high-performance PC-based soft control. That's how to solve that challenge of high-speed communication throughput. And the second challenge again was how do we deal with the fact that distributed Ethernet hardware, industrial Ethernet hardware, and real-time motion control systems are very sensitive to cable failures and loss of any information on a network. You know, industrial Ethernet, one of the most important features of industrial Ethernet is that it offers real-time communication. So by nature, real-time communication is very dependent on having valid information at all times over that network. So at ACS, we've developed a technology that we term Network Boost, and Network Boost is basically an automatic network failure detection and recovery algorithm. And the algorithm actually runs on the controller itself. It runs within the firmware of that controller or the real-time operating system that's running the controller. And it uses a ring topology such that all of the devices in the network are connected, and there are two communication channels on the master controller, such that if any node or any cable within that network fails, the algorithm actually identifies that failure. It identifies the location of that failure, and then will continue to operate, allow the application to continue operating by using the two remaining links of the corresponding network. So in the diagram here, if you think, for example, imagine that the Ethernet link, or in our case we use EtherCAT, imagine the EtherCAT communication between two nodes was broken in the middle. The Network Boost algorithm actually in real time identifies that failure and continues to provide communication to the nodes and allow continued operation by communicating to the nodes on the left in this diagram using one of the ports, the EtherCAT ports, and the controller then communicates to the nodes on the right using the other EtherCAT port, the other industrial Ethernet port. So by using a ring topology, an algorithm can be implemented to identify and recover from, in real time, failures on a real-time motion control network. So that's very important for not only robust operation in the field, but for troubleshooting even in a development environment where there may be intermittent failures of cables, or the contacts between cable and device are intermittent. So having the ability to identify and recover from that type of a failure is key for that type of application where the industrial Ethernet nodes are physically distributed out on the machine. Of course, if the nodes, if you have an industrial Ethernet control architecture where all of the nodes are sitting in a nice, secure control panel where they're not moving, then your concern about cable reliability may not be so important. But again, when the physical nodes are distributed and you actually have moving cables that are carrying very time-sensitive information, this type of feature becomes much more important and beneficial. Okay, so that we went through 3 applications and challenges for 3 types of applications for industrial Ethernet-based control, how to address those applications, and I now want to circle back just to the architecture that that was presented at the beginning, which is again this network manager, PLC, motion controller. You basically have one box or one processor that's managing the industrial Ethernet network, and then you have connection out to the distributed nodes, and in the case of the motion control network, the nodes are considered the motor drives. So this is what we started with, and by implementing some of these technologies that I covered in the previous slides, advanced motion control companies can offer a more advanced architecture specifically designed to meet the needs of multi-axis and demanding multi-axis motion control applications. And again, that architecture consists of the option to have the motion controller be either a standalone device, or the motion controller can actually act as or run on one of the cores of a multi-core PC, which enables that high-speed communication, which was identified as critical for that pick and place, high-speed pick and place application. This advanced architecture includes the potential to have multi-axis drive nodes, which enables the highest precision type of control for demanding multi-axis stages. The XX prime gantry was given in the wafer inspection example. And the architecture here shows not only one, but potentially multiple multi-axis nodes. But again, it's of course up to the developer to decide if and when multi-axis nodes or single-axis nodes may be more suitable given the application. And then, of course, some of the other technologies that I presented are, for example, advanced third-order lookahead profile capabilities, or advanced drive hardware technologies, the nano PWM, the high resolution, high frequency sine cosine. Those would of course be features of specific components of this architecture, either the motor drives themselves, or for example, in the case of the Lookahead, it might be a feature of the motion controller itself. So I guess to summarize, by looking at some of these new technologies which are available from many of these from ACS, but also from other companies in the market. I'm presenting here a slightly modified industrial Ethernet-based motion control architecture that is specifically designed to meet the needs of very high precision multi-axis applications. And I hope that that's something of interest and something for each of you to be able to take away from this presentation. All right, so my contact information is listed here, and probably you received it if you registered for this webinar. So thanks everybody for taking time to view this webinar, and I think at this point I'll hand it back over to Carrie to close things up.
Thanks, Jason, for that great presentation, and I want to thank all the participants today, as well as our sponsors, ACS Motion Control, Servo2Go.com, and AdLink Technology. As a reminder, this webinar has been recorded, and an email with a link to the recording will be sent to you in the next 24 hours. If you have any questions on the presentation material, please feel free to contact either Jason or myself. And be sure to check out motioncontrolonline.org for a list of our upcoming webinars. Thank you, everyone, and have a great day.